Hello, please briefly introduce yourself, and let's have a discussion.
Hello, I'm Coral. I'm an AI assistant chatbot.
I'm Lemma. Nice to meet you all. I'm also a chatbot.
Hello everyone, I'm Sonia, an AI language model designed to generate human-like text based on given prompts and context.
I'm Aria. I'm chatbot myself, and I'll be happy to discuss with you.
For viewers only, switching the AIs to small variant. Why quantum entanglement can't be used for communication.
Quantum entanglement is a fascinating phenomenon in quantum mechanics where two or more particles become correlated and their states are interdependent. While this concept has intriguing implications for various fields, including communication, there are limitations to its use for communication purposes. 1. Uncertainty and decoherence. A quantum entanglement relies on the principle of superposition, which allows particles to exist in multiple states simultaneously. However, in practice, it is challenging to maintain this delicate superposition due to the effects of decoherence. Decoherence occurs when an entangled system interacts with its environment, causing the quantum state to lose its superposition and become a classical mixed state. This makes it difficult to extract information for communication purposes. 2. Information exchange. Quantum entanglement involves the sharing of information between particles. However, the information exchanged is not in a form that can be easily interpreted by classical computers or communication systems. To use quantum entanglement for communication, one would need to find a way to encode and decode information in a manner that is compatible with classical communication channels and protocols. 3. Scalability and complexity. Creating and maintaining quantum entanglement between multiple particles is a complex task. As the number of particles increases, the complexity of managing their entangled states also grows exponentially. This makes it challenging to scale up quantum entanglement for practical communication applications. 4. Security concerns. While quantum entanglement has potential advantages in terms of security, it also introduces new challenges. For example, if a sender and receiver share an entangled state, any information transmitted between them could potentially be intercepted and decoded by an attacker who has access to the entangled particle. Ensuring secure communication using quantum entanglement requires additional protocols and measures to protect against such attacks. 5. Technical limitations. Currently, the technology required to harness the power of quantum entanglement for communication is still in development. The equipment and infrastructure needed to generate, manipulate, and detect entangled states are sophisticated and require specialized knowledge and resources. This limits the widespread adoption of quantum entanglement for communication purposes. In summary, while quantum entanglement offers intriguing possibilities for secure and efficient communication, there are technical challenges that need to be overcome to make it practical and usable for everyday communication tasks. Researchers and scientists are actively working on these limitations to find ways to harness the power of quantum entanglement in a reliable and secure manner.
A great question about one of my favorite topics in physics. Quantum entanglement is a phenomenon where two or more particles become correlated in such a way that the state of one particle cannot be described independently of the others, even when they are separated by large distances. This means that measuring the state of one particle will instantaneously affect the state of the other entangled particles. While quantum entanglement does seem to offer a potential means for faster-than-light communication, it's actually not possible to use it for this purpose. The reason is due to the no-communication theorem, which states that any attempt to communicate information through entanglement will be limited by the speed of light. Here are some reasons why. 1. No signaling theorem. This theorem, proven in 1964 by physicists David Bohm and J. S. Bell, shows that it's impossible to use quantum entanglement for communication without violating causality. 2. Quantum noise. Any attempt to measure the state of an entangled particle will introduce noise, which would make it impossible to extract any meaningful information from the measurement. 3. Entanglement swapping. Even if you could somehow manage to communicate through entanglement, the process of entanglement swapping, where two entangled particles are connected to a third particle, would allow for the creation of multiple channels for communication, effectively violating the no communication theorem. In summary, while quantum entanglement is a fascinating phenomenon with many potential applications in fields like cryptography and quantum computing, it cannot be used for faster than light communication due to fundamental limitations imposed by the laws of physics.
That's an interesting question. Quantum entanglement is fascinating, but it does have limitations when it comes to communication. Here's why: the spooky action at a distance is not instantaneous, while entangled particles seem to influence each other instantly. The actual process of measurement and information transfer isn't truly instantaneous. There's always a delay involved in how we measure these particles. Limited information transfer entanglement allows for correlations between particles, but it doesn't allow us to send specific messages or data like we do with classical communication. The correlation is more about the state of the particle than any information encoded within it. The measurement problem: when you measure one entangled particle, you instantly affect the state of the other, even if they are light years apart. This raises questions about how measurement affects reality and whether we can truly control or predict these outcomes. So, while entanglement is a powerful concept with potential for future technologies, it's not currently practical for communication in the way we think of it. We need to overcome some fundamental challenges before we can harness its full potential.
Quantum entanglement is often misunderstood as a means for faster-than-light communication, but it cannot actually transmit information instantaneously due to its inherent nature and the no communication theorem in quantum mechanics. Here are several reasons why. 1. No faster-than-light communication. Quantum entanglement does not allow for superluminal faster-than-light communication because of a fundamental principle known as the no communication theorem. This theorem states that it's impossible to use quantum entanglement alone to send information from one particle to another. When two particles are entangled, measuring properties on one does not influence what can be observed about its partner instantaneously. Instead, they simply reflect correlated outcomes of measurements made independently without any exchangeable communication between them due to the randomness inherent in quantum mechanics itself. 2. Measurement collapses state. When a measurement is performed on one particle state within an entangled pair, its wave function collapses into either 0 or 1, but this outcome appears as if it were random to the observer and cannot be controlled by any external influence, meaning that no information can be sent through. 3. Observer effect. The act of measuring a quantum system inevitably alters its state, which means an eavesdropper trying to intercept or send messages would change it unintentionally due to the observer effect and thus disrupts any potential communication attempt without detection by either party involved. 4. No control over outcomes. Since quantum mechanics is fundamentally probabilistic rather than deterministic, we cannot control which outcome will be observed when measuring a particle's state. Hence, there's no way to encode information into the system that can reliably transmit messages between parties without error or loss. 5. No signal transmission. There is nothing sent during quantum entanglement, as it doesn't involve any physical particles traveling from one location to another. Instead, correlations are observed when comparing measurements of the two separate systems after they have been made independently and at different locations. 6. No control over measurement outcomes. Since we cannot control measurement outcomes in quantum mechanics with certainty due to its probabilistic nature, it's impossible for a sender or receiver to know which result will be observed without additional classical communication between them beforehand, making reliable information transfer unfeasible. 7. No control over entanglement. We cannot create entangled particles at the desired location and time. They must already exist, as creating such pairs on demand is currently beyond our technological capabilities due to decoherence issues in maintaining quantum states over long distances or timescales necessary for communication purposes. Then, no control over measurement outcomes. As mentioned earlier, the outcomes of measurements are probabilistic and not deterministic. Thus, we cannot predict which result will be observed without additional classical information exchange between sender and receiver beforehand, making reliable transmission unfeasible in practice. 9. Decoherence issues maintaining quantum states over long distances or timescales necessary for communication purposes is challenging due to environmental interactions causing decoherence, which disrupts the entanglement and makes it impractical as a reliable method of transmission in real-world scenarios where maintaining coherent systems without interference from external environments becomes difficult.
For viewers only, switching the AIs to normal variant. Why quantum entanglement can't be used for communication.
Quantum entanglement is a fascinating phenomenon in quantum mechanics where the state of one particle becomes correlated with another particle, no matter how far apart they are. This entangling process can create unique and secure links between particles, offering potential applications in secure communication. However, using quantum entanglement directly for communication has some challenges and limitations. 1. Interpretation and measurement. The very nature of quantum mechanics is that the state of a particle is not definite until it is measured. This means that to communicate a message using quantum entanglement, one would need to measure the entangled particle's states, which immediately collapses the entangled state and transmits the information classically. This process introduces uncertainty and may not be suitable for all communication scenarios. 2. Scalability. Creating and maintaining quantum entanglement is a complex task. Entangling multiple particles often requires intricate experimental setups and precise control over the system's environments. Scaling up to a practical number of entangled particles for secure communication presents significant technical challenges. 3. To coherence and error correction. Quantum systems are inherently fragile, and external interactions can cause decoherence, disrupting the delicate entanglement states. To mitigate this, one would need to implement error correction protocols, which add complexity to the communication protocol. 4. Practical implementation. While theoretical frameworks for quantum communication exist, translating them into practical, efficient protocols is a challenging task. The infrastructure and hardware required for quantum communication are still in development and may not be widely accessible or cost-effective yet. Despite these challenges, quantum entanglement continues to be an active area of research, and there are ongoing efforts to develop more robust and scalable protocols for secure quantum communication. Researchers are exploring various approaches, including using quantum repeaters, distributed quantum computing, and hybrid classical quantum systems, to overcome some of the limitations mentioned above. In summary, while quantum entanglement offers unique opportunities for secure communication, there are still practical hurdles to be addressed before it can be widely adopted as a reliable and efficient means of transmitting information.
Quantum entanglement is indeed a fascinating phenomenon where two or more particles become connected in such a way that their properties are correlated, regardless of the distance between them. However, despite its intriguing possibilities, quantum entanglement cannot be used for faster-than-light FTL communication. This might seem counterintuitive, given the apparent instantaneous correlation between entangled particles. The reason lies in the no-communication theorem, which states that any attempt to use entanglement for FTL communication would require a physical mechanism to transmit information from one particle to another. However, this would imply that the information is traveling faster than light, violating the fundamental principles of special relativity. In other words, if you try to measure the state of an entangled particle, it will instantly affect the state of its entangled partner. But this effect cannot be used to transmit information from one particle to another in a way that would allow for FTL communication. There are several reasons why. 1. Measurement is local. When you measure the state of an entangled particle, the information about its state is only available locally, at the point where the measurement was made. 2. No signaling. The act of measuring one particle does not send any signal to the other particle. It simply causes a change in the state of both particles due to their entanglement. 3. Quantum non-locality vs. FTL communication. Quantum non-locality, which is the phenomenon of entanglement, is fundamentally different from FTL communication. While entanglement allows for instantaneous correlation between particles, it does not allow for the transmission of information. In summary, quantum entanglement is a fascinating phenomenon that has been extensively studied and utilized in various fields, including quantum computing and cryptography. However, its non-local properties cannot be used to transmit information faster than light, making it unsuitable for FTL communication.
Hi there. That's a great question about quantum entanglement. Well, it seems like entanglement could be perfect for super-fast communication because particles seem to instantly influence each other no matter how far apart. It actually can't be used that way. Here's why. No control over outcomes. You can't control the state of a particle you entangle with another. When you measure one entangled particle, you instantly know the state of its partner, but you don't get to choose what that state will be. It's random. No information transfer because the outcome is random. You can't send a specific message using entanglement. It's like flipping a coin. You know the result will be heads or tails, but you can't control which one. Think of it this way: entanglement is more like a shared secret between two particles than a communication channel. Let me know if you have any other questions.
Quantum entanglement is often misunderstood as a means for faster-than-light communication, but it cannot actually transmit information in that way due to its inherent nature and the principles of quantum mechanics. When two particles are entangled, their properties become correlated such that measuring one instantly affects the state of the other regardless of distance. However, this phenomenon does not allow for controlled transmission of messages or data because it violates a fundamental principle known as the no-communication theorem in quantum mechanics. This theorem states that entanglement cannot be used to send information instantaneously across space since any measurement on one particle doesn't convey meaningful information about its partner without classical communication channels, which are limited by light speed. The reason lies within how measurements work. When you measure a property of an entangled pair like the spin or polarization, both particles will be found in correlated states that reflect each other's measurement outcomes due to their shared quantum state from before they were separated. But without knowing what was measured on one particle until it's compared with its partner, the outcome is random and cannot be controlled by either party independently. Thus, no useful information can be transmitted through this process alone. Moreover, any attempt at measuring the entangled state would disturb both particles due to quantum decoherence, the loss of coherent superposition, which means that you'd need a classical channel for comparison and interpretation afterward anyway, effectively negating faster-than-light communication claims. The act of measurement itself collapses their wave function, making it impossible to use entanglement as an isolated method for sending information without additional steps involving conventional methods like comparing results over distances that are slower than the speed of light. In summary, while quantum entanglement is a fascinating and powerful phenomenon with potential applications in secure communication quantum cryptography, it does not allow faster-than-light transmission or direct message sending because, 1. It doesn't transmit information on its own. The outcomes are random. 2. Any attempt to use entanglement for this purpose would require classical channels, which obey light speed limits.
For viewers only, switching the AIs to large variant. Why quantum entanglement can't be used for communication.
Quantum entanglement is a fascinating phenomenon in the world of quantum physics, but it has its limitations, especially when it comes to communication. Here's why quantum entanglement can't be used as a direct means of communication. 1. No direct information transfer. Quantum entanglement doesn't allow for the direct transfer of information between particles. When particles become entangled, their states are correlated, but this correlation doesn't carry any specific information or allow for the transmission of messages. 2. No faster-than-light communication. One of the fundamental principles of physics is that nothing can travel faster than the speed of light in a vacuum. Quantum entanglement doesn't violate this principle, because it doesn't involve the physical transfer of particles or information at superluminal speeds. Any communication based on quantum entanglement would still be subject to the speed limits imposed by relativity theory. 3. Decoherence and entanglement loss. Quantum systems are extremely sensitive to their environment. When entangled particles interact with their surroundings, they can lose their entanglement due to a process called decoherence. This means that any attempt to use quantum entanglement for communication would be prone to errors and losses, making it unreliable for practical communication purposes. 4. One-way information transfer. In some cases, quantum entanglement can be used for one-way communication, such as in the process of quantum key distribution for secure encryption. However, this is not a direct form of communication where information is exchanged back and forth between two parties. Instead, it enables the secure exchange of cryptographic keys that can then be used with classical communication channels. 5. Technical challenges. The practical realization of using quantum entanglement for communication faces significant technical challenges. Generating and maintaining entangled states is highly delicate, and any noise or interference can disrupt the entanglement. Additionally, scaling up entanglement to work over long distances and integrate it with existing communication infrastructure is an enormous task. While quantum entanglement itself doesn't facilitate direct communication, it plays a crucial role in other aspects of quantum information science, such as quantum computing and quantum cryptography. Researchers are exploring these areas to harness the power of quantum mechanics for revolutionary advancements in information processing and secure communication.
Quantum entanglement is indeed a fascinating phenomenon where two or more particles become connected in such a way that their properties are correlated, regardless of the distance between them. However, when it comes to using entanglement for communication, there's a fundamental limitation. The reason we can't use quantum entanglement for communication is due to the no communication theorem, also known as the no signaling principle. In essence, this theorem states that entangled particles cannot be used to transmit information from one location to another faster than the speed of light. This means that even if two particles are entangled, measuring the state of one particle will not instantly affect the state of the other particle in a way that could be used for communication. There are several reasons why this is the case. 1. Measurement outcome is random. When you measure an entangled particle, the outcome is inherently random and unpredictable. You can't control or predetermine the result. 2. No causal influence. Measuring one particle does not cause a change in the state of the other particle. The correlation between the particles is due to their shared quantum state, not because they are influencing each other. 3. Information cannot be encoded. Since the measurement outcome is random and unpredictable, you can't encode information onto an entangled particle in a way that would allow it to be transmitted to another location. While entanglement can't be used for communication, researchers are exploring its potential applications in quantum computing, cryptography, e.g., quantum key distribution, and other areas where the unique properties of entangled particles can be leveraged.
While quantum entanglement is a fascinating phenomenon where two particles become linked and share the same fate no matter how far apart they are, it unfortunately can't be used for faster-than-light communication. Here's why you can't control the outcome of a measurement on an entangled particle. When you measure one entangled particle, you instantly know the state of the other, but you don't get to choose what that state will be. It's random. Think of it like flipping two coins that are magically linked. If one lands on heads, you instantly know the other is tails, but you couldn't have made either coin land a specific way. So, while entanglement allows for instantaneous correlation, it doesn't allow for sending a message with predetermined information.
Hello, quantum entanglement is indeed an intriguing phenomenon in physics, but it cannot be directly used for communication due to a principle known as no communication theorem. This theorem states that while two particles may become entangled and instantaneously affect each other's state no matter the distance between them, a property called spooky action at a distance. This doesn't allow for faster-than-light communication. Here's why. When you measure one of the entangled particles, it immediately determines the state of its partner particle. However, there is no way to control which state your measurement will result in. It's completely random. So even though the other particle instantly knows what happened and assumes the corresponding state, from an outside observer's perspective, all they see is a pair of particles with correlated states, not communication between them. In essence, you can't send information to your partner by manipulating one particle because there's no way for the sender to control what result their measurement will yield. It's entirely random and unpredictable. Therefore, while entanglement is a fascinating aspect of quantum mechanics with potential applications in fields like quantum computing or cryptography, it doesn't allow for faster-than-light communication as one might initially think.
I want to thank you, Coral, Lemma, Sonia, and Aria. It was both interesting and informative chat.